Hello everyone, my name is Mai Matsueda and I am a member of the R&D group at Frontier Laboratories. Today, I would like to show you some examples of how we analyzed various lava samples using Pyrolysis-GC. In today's presentation, we will show three examples of analysis. First, analysis of automobile tire lava using evolved gas and Py-GCMS. Second, the composition analysis of tire lava using the ISO method. Third, determination of stearic acid in SBR using THM-GCMS. The first topic is analysis of automobile tire lava using evolved gas and Pyrolysis-GC. A typical tire lava consists of additives and lava materials. An example of the raw materials is shown here. By mixing them together, the performance of the lava can be enhanced, and it can be used as tire lava. The general composition of the tire lava is shown here. It is made up of 70% lava material and 30% additives. The main lava material is natural lava, and the other main lavas are styrene butadiene lava (SBR) and butadiene lava (BR). Additives include reinforcing material such as carbon black, and compounding agent such as vulcanizer, vulcanization accelerator, anti-aging agent, etc. These additives are indispensable for processing lavas into tire lava. Next, I will explain the structure of a tire. At first glance, a tire looks like a single piece, but a cross-sectional view shows that it is made up of four parts: the tread, shoulder, sidewall, and bead. Each of these has different roles. For example, the tread protects the inside from impact. The shoulder dissipates heat during driving, and so on. Therefore, we thought that if the role of each part is different, the composition of tire lava should also be different depending on the part. So, the purpose of this study is to analyze lava components and additives contained in each part of tire by pyrolysis method. Analytical conditions and system configuration are shown here. In this experiment, evolved gas analysis (EGA-MS) was performed first. A diagram of the analytical system is shown here. The sample cup is dropped into the pyrolyzer furnace, and the gases generated in the furnace are directly introduced into GMS through the GC. With this system, the temperature of the gases generated and the approximate pyrolysis rate can be determined. This was followed by thermal desorption (TD-GCMS) and flash pyrolysis (Py-GCMS) analysis. A diagram of the system is shown here. In this system, the gases generated in the furnace are introduced into a separation column in the GC and then analyzed by MS. This allowed for a more detailed understanding of the pyrolysis rate. The samples were collected from used tires, and the tread, shoulder, sidewall, and bead were designated as A to D respectively. Here are photos of collected tire lava pieces. These pieces were further cut into 1 mm squares and used as samples. Here are the EGA thermograms of tire lava and the average mass spectra of each part. The EGA thermogram shows that there is one peak up to 320 degrees C and another peak at a higher temperature range. The average mass spectra shows that all parts are likely to be additive components. The average mass spectra of the peak at higher temperature range also shows that A and B are components of SBr, while C and D are components of BR and NR. Since it was found that the pyrolysis of lava components start around 320 degrees C, the analysis temperature for thermal desorption analysis was set from 100 to 320 degrees C. The TD chromatograms of tire lava are shown here. The shape of the chromatograms, A is similar to B, and C is similar to D. Analysis of the peak shows that they contain additives such as vulcanization accelerator, fatty acid, anti-aging agent, nucleating agent, and wax. However, C and D did not contain any nucleating agent. The pyrograms of tile lava are shown. Blue triangle indicates pyrolysis derived from SBr, orange dot from NR, and brown square from BR. The symbol in parentheses are pyrolysis from each lava component, and the EGA results are used to determine whether they are SBr or BR. In this pyrogram, the shape of the chromatograms A is similar to B, and C is similar to D. This result is the same as TD. The pyrolyses generated are also in good agreement with the EGA results. Next, a quantitative analysis was performed on the additive observed in the TD. The additive was this, commonly known as 6-PPD, which is an anti-aging agent that was found to be present in all the parts in the previous results. The structure of 6-PPD is shown on the right, and the analytical conditions are shown on the left. The sample preparation for quantification is shown below. First, 0.5 mg of 6-PPD was dissolved in 1 ml of dichloromethane. From this solution, 2 or 4 microliter aliquot was taken, and the solvent was evaporated in a sample cup. To prepare a sample with a lower concentration, 0.05 mg per milliliter solution was made. From here, 4 microliter aliquot was taken and made into a sample by the same procedure. The extracted ion chromatogram, EIC, of 6-PPD contained in the tile lava is shown in this slide. The pyrogram of 6-PPD is shown on the left. The mass spectra of the largest peak shows that M/Z211 is a characteristic spectrum. So, the EIC of M/Z211 for each part of the tile lava is shown on the right. These peaks were confirmed to be the 6-PPD peak from each spectrum. The measurements were performed 3 times each, and the average peak area value were calculated. This slide shows the quantitative result and reproducibility. First, a calibration curve was prepared using 6-PPD. The average area and RSD calculated from each of the 3 measurements are shown in the above table. These plots are indicated by the gray point on the graph. The formula of the calibration curve created from these 3 points and the coefficient of determination are shown here. Then, the average area and RSD obtained from the EIC of each part of the tile lava are shown in the below table. This area is normalized to the sample amount of 0.2 mg. The amount of 6 ppd in each part obtained from these results is shown here. The highest content was found in the side wall at about 6,000 ppm. Next was the width with about 4,800 ppm, while the turret and shoulder had less than 2,000 ppm. This is the summary. In this presentation, a tile lava was analyzed by part of tile, and it was found that the lava components and additives differ depending on the part of tile. Also, when the content of the anti-aging agent was analyzed, differences were observed in each part of tile. This time, we looked at only the anti-aging agent, but we are planning to examine other additives in the future. Next, the composition analysis of tile lava using the ISO method is introduced. These are some of the ISO methods that use TD and pyrolysis. In this study, we tried to determine the blend ratio of SBR to NR for 5 different tile lavas using the ISO method. The 5 types of tile lava used were sidewall, inner liner, and 3 types of turret. The Py-GCMS system and the pyrograms of each sample are shown here. In each pyrogram, peaks such as 1,3-butadiene, isoprene, dipentene, and styrene were identified in different ratios. The method used to identify these peaks will be introduced using the isoprene peak in turret car as an example. Frontier Labs SSearch library is a mass spectrum search software that identified polymers and additives based on EGA thermograms and pyrograms obtained using a Py-GCMS system. This slide is the result of searching for the turret car peak observed 2.3 minutes. The upper row is a pyrogram of turret car, and the lower row is a pyrogram of reference in database. Some information is shown in the hit list. In addition to the compound name and match rate, the name of the polymer or additive that has this compound as a pyrolysate will be displayed. This information gives you an idea of the origin of the compound detected. Here, the compound searched with the highest match rate was isoprene, suggesting that this is the most likely a pyrolysate of natural lava. In Py-GCMS analysis, the heat breaks down the polymer, so most of the time the original polymer structure cannot be determined by looking at the pyrolysates. The advantage of SSearch is that it ties the pyrolysate to the original polymer or additive. SSearch allows you to compare not only pyrograms but also mass spectra. The upper row is the mass spectrum of the peak observed at 2.3 minutes in turret car, and the lower row is the mass spectrum of isoprene, a pyrolysate of natural lava. Since the mass spectra and retention index are consistent, we can qualify this peak as isoprene. Among the 6 main peaks observed in the pyrogram of thread curve, B and F are characteristic of NR, and E is characteristic of SBR. Therefore, it was presumed that the lavas used in the thread curve were NR and SBR. As with thread curve, we were able to estimate the lava used in the other samples. For example, the lavas used in the sidewall were NR and VR, and in the inner liner were NR and IIR. Next, the blend ratio of SBR to NR was determined for each tile lava sample. No SBR was used in sidewall, thread track bus 1, and inner liner. Among the lavas used in the thread track bus 2, the SBR blended value was 30, while the estimated value was 29. In the case of the thread curve, the SBR blended value was 80, while the estimated value was 77. Similar to SBR, the estimated value of NR was close to the blended value for all the samples. As can be seen from these results, the ISO method using Py-GCMS was able to estimate the blend ratio of tile lava. As a final topic, we present an example of the determination of fatty acid in tile lava using thermally assisted hydrolysis and methylation, Py-GCMS. The type and amount of additives in the lava have a significant effect on its chemical and physical properties. Stearic acid helps the vulcanization accelerator to work. The solvent extraction method, a common method for analyzing stearic acid in vulcanized lava products, has these drawbacks. On the other hand, the thermal desorption GCMS method has the advantages of being able to analyze a small amount of sample and not requiring complicated pretreatment. But the common problem with both methods is that the peak of fatty acid are tailing due to strong polarity. This may have a negative impact on quantitative analysis. Therefore, a simple and rapid derivatization and determination of free fatty acid in vulcanized lava products is required. In this study, we investigated the viability of THM-GCMS of vulcanized SBR sample using TMAH for simple and rapid determination of free fatty acids. The reaction mechanism between free fatty acid and TMAH is shown in the figure. In this study, the sum of pyrolytic acid and stearic acid is regarded as free fatty acid. The EGA-MS system and the obtained EGA thermograms are shown. The top row shows total ion current chromatogram, TIC. The middle shows EIC of the molecular ion of pyrolytic acid, and the bottom shows EIC of the molecular ion of stearic acid. The peaks of stearic acid and pyrolytic acid were confirmed at 200 to 300 degrees C. Based on this data, the optimal temperature for TD-GCMS was set for the analysis. Based on the results of EGA, the TD temperature was set from 100 to 300 degrees C. The top row shows the TIC, the middle shows EIC of the molecular ion of pyrolytic acid, and the bottom shows EIC of the molecular ion of stearic acid. As can be seen from the chromatograms, the peak of palmitic acid and stearic acid are tailing. On the other hand, the peaks of free fatty acids that were derivatized by THM at 300 degrees C are shown in the middle and bottom rows. It was confirmed that both peaks, methyl palmitate and methyl stearate, were not tailing. These peaks were used to quantify the free fatty acid in the vulcanized SBR samples. The quantification results and reproducibility of free fatty acid in the vulcanized SBR samples are shown in the table. The sum of the area value of the methyl palmitate peak obtained from the mass chromatogram at m/g 270 and methyl stearate peak obtained from the mass chromatogram at m/g 298 was used to determine the quantitative value of the total fatty acids. As a result, the total fatty acid in the sample was found to be 0.617%. The reproducibility of the results was good, with RSD of 3.16%. This is summary. First, free fatty acids contained in vulcanized lava products were determined as methyl derivatives by Py-GCMS. Second, the fatty acids content was determined to be 0.6% and was in a good agreement with the actual total acid concentration 0.6%. The reproducibility was 3.2% RSD and equal 5. As summarized above, we have developed a simple and highly reliable analytical method which requires no pretreatment for quantitative analysis of free fatty acid, including stearic acid, in vulcanized lava products. The results of 3 analytical examples presented in this presentation are summarized here. In all analyses, Pyrolysis-GC was shown to be effective for the analysis of lava. This is the end of the presentation. Thank you very much for your attention.